Great, feel free to take it away.
Okay, great. Thanks, Liam. Yeah, so when I got the chance to give a talk on an MR group talk in September, I thought it would be a good opportunity for new students to give a little bit of an overview of the Bruker systems, because I think sometimes people don't even know that they're here. And then also I've been the manager of the Bruker system. So if you don't know me, I'm the one to contact if you're interested in them. And I've been in that position for about a year, and I've kind of learned a few things over the course of the year that maybe are of interest for people who are already using the scanner as well. So yeah, I'll give an overview of the two systems that we have and talk about how some of the groups are using them currently. And then I'll give a little bit more detail about some of the coils that are available, about B0 and shimming methods, and about some things about the gradients that I've learned. So we have two systems. On the left, you see the 70 horizontal bore system that's on S-ground. So there are beds that attach here, and then they automatically advance into the scanner. So the system is the Bruker BioSpec system, and the hardware is this Advanced 3 console. And on S4, maybe a little bit less well-known, hidden away, there's a 70 vertical bore system. So the samples go in on the bottom here. And this is the Bruker Ascend system. And it has this slightly newer hardware, Advanced 3 HD, which is what you see in these cabinets here. The system also converts, you can take the gradients at the bottom, the imaging gradients, and put a shim stack into the top and do NMR spectroscopy with this system as well. I do think it's interesting. So if you do your talk on MS Office, apparently it automatically generates captions via, I guess, some sort of AI. So it describes this image as a large white machine in a room, and the vertical bore as a white cylinder with blue legs and handles, which I guess is relatively accurate. So a little bit more detail on these systems. I'll talk in more detail about the gradients later, but the basic point here is that there are two setups for the S-ground system. The way it's normally set up is with this GA12S gradient. So this is a slightly stronger gradient system, and the volume coil that goes inside of here is a little over 8 centimeters. So this is the setup that is normally used by most groups who are scanning mice and rats. But it is possible to take this gradient insert out, and then you have a slightly weaker gradient system here. And the volume coil that goes in there gives you about 15 centimeters of space to work with. So some groups that are doing more obese rats might need to use this system. It's being used for guinea pigs right now, and no one's currently using it for rabbits, but they should fit in this system as well. And then the vertical bore system, despite being named the 300 WB, so it's a wide bore system, has the smallest diameter, so it's about 3 centimeters inside the volume coil, and the strongest gradients of 1500 millitesla per meter. So most of what the system has been used for so far has been phantoms, people testing out nanoparticles, a little bit of in vitro cell work, and some ex vivo tissue samples. But Daniel Jayakarsana has been working on setting it up to scan mice. So you can fit mice into the system, but then they're sort of hanging vertically. So we're working both on ways to support the mice so that they can be relatively comfortable in there, and then also running the anesthetic and animal monitoring system into the much narrower bore. So I think we're relatively close to getting this set up, and it's not going to be ideal for everyone who's already scanning on S-ground, but the S-ground system is much busier and much more fully booked, and it's possible that some groups might be able to move to the system when that happens. And as I mentioned, the system does convert to do NMR spectroscopy. I'll talk a little bit more about coils later, but just to give you an idea, so there are sort of Bruker branded coils that are automatically represented by the system, and then there are a few groups that have built their own coils. So both setups have their own volume coil, which is a proton transmit receive coil. And then normally to get enough SNR, you would combine this with some kind of proton receive coil, and I'll show you a few of the examples that we have for that. You might not know, because I don't think anyone is currently using this, but we do have a dual proton carbon-13 Bruker coil for the S-ground system, which is a transmit-receive surface coil. And then Angus Lau's group built a deuterium surface coil, and Peter Trong has been working on several surface coils, including some larger ones for proton. And then on the S4 scanner, there's a volume coil for proton, and then also a dual proton 31P coil. And then if you have something really small that you need to scan, your best bet is probably to use the S4 scanner with this 10 millimeter proton surface coil. As far as I know, these are different connections, so I don't think you can sort of exchange the coils between systems, but I did want to note that they both run the same version of Paravision. So there are a few groups looking at pulse sequence programming, or even if you just wanted to do a little bit of a check of some of your data, you can bring it up on the S4 scanner, which, because it's not as fully booked, is probably a little bit easier. Because of the gradients, if you're setting up like a protocol, your sequence timings won't be exactly the same, but anything that compiles on the system on S4 should also compile on the system on S-ground. So that's an option. So I'll talk mostly today about the S-ground setup because it is what most people are using. So just to let you know what's available if you're interested in animal imaging. If you're running shorter scans, you would probably use an injected anesthetic, but for longer scans, there is inhalable anesthetic that's available for group use. That's part of the booking fee. So there's an induction chamber to put the animals under before they go into the scanner, and then you switch everything over so that the anesthetic is running into the scanner via a bite bar or nose cone system, and the animals will stay under while they're being imaged. And then there's a vacuum system for scavenging. There are several restraint devices, so you can use ear bars or face clamps just to keep the head steady if you're doing head imaging and want to avoid some respiratory motion. There's a water blanket to keep the animals warm while they're being scanned. I did note here that there is an air system available. No one's currently using it, but if for some reason you can't use the water system or you're getting some kind of flow artifacts or something, let me know and we can look at setting this up. And then there's a monitoring system, so that's what's shown in the image on the right here. This orange line on the bottom is a temperature monitor that runs from a temperature probe that's either under the animal or inserted rectally. And you can change the temperature on the water blanket from the console, so you don't have to go in the room to keep the animal's temperature steady. Then up above that, you see the respiratory trace where the animal is breathing. So you can gate to this if you have respiratory motion issues. And then there's also ECG monitoring. So I think currently Moses is the only one using this. You have to bring your own ECG leads. So we have the system to connect everything to and do triggering if that's what you're interested in. But the leads come with the animal. So I'm not going to talk in too much detail about some of the work that I'll show, but there are groups doing a lot of different things. So I just wanted to give some idea of what you can do on the scanner. But you'll probably see a lot of other MR group talks or student seminars about some of this work. So there are a number of groups using the MR system to target focused ultrasound. This is work from Paige Smith and Megan O'Reilly's lab in rat spinal cord. So they put the rat on its back on this little fuss table that they have, and then they put the fuss table into the scanner, and they acquire like images like these of the rat spinal cord. And then they bring the animal out of the scanner, and the fuss table transfers over top of their transducer, and they can bring the MR images up, and they can say to the transducer to target specific places. So these 4 cells here are the areas that they're targeting with their ultrasound. And this disrupts the blood spinal cord barrier and allows things to cross it. So they're interested in the delivery of this drug, trastuzumab, but also to check that they did actually disrupt and they're targeting the area that they want to. Afterwards, they inject gadolinium, which is an MR contrast agent. And you see these slightly hyperintense areas here to indicate that, yeah, they did disrupt the blood spinal cord barrier. This is work from Il-Sung Ju and Bojana Stefanovic's lab, looking at blood flow in rats. So these are rat brains, and they use a technique called arterial spin labeling, where they label the blood and then watch how it flows into certain areas of the brain. And in this case, they were looking at differences in flow when they were stimulating the forepaw. So even though the rat is anesthetized, they could still stimulate the forepaw, and this changes the blood flow. So in green, this is for normal rats, normal Fisher rats, and then in orange is a transgenic model of Alzheimer's disease, and you can see that there's a difference in blood flow in these 2 cases. So this is a little bit different. This is work from Chung Lee's lab, and they're looking at the structures of the inner ear. So they put contrast agent into the mouse ear before it goes in the magnet, and they use a magnetic system to like move it into the mouse's ear, and then they acquire MR images in slices and reconstruct these volumes to look at the structures. So the images on the left are from a wild-type mouse, and then on the right, this is a knockout mouse, a model of rickets that mimics some of the features of progressive hearing loss. So what you see here is this much more flattened structure, and that's because there's a structure in between that's enlarged and is compressing this area. And then I want to show something that isn't like standard proton 1H. So this is some of that deuterium work from Angus Lau's lab in vitro. So each of these tubes is filled with cells, in this case, leukemia cells, and they're looking at the metabolism. So they use this deuterated glucose, and then they look at how the cells metabolize it over time, particularly the production of lactate. So when these cells are treated with a chemotherapy drug, you see that 24 hours after treatment, they're pretty similar to the controls, but 48 hours after the cells start to die, there's much less lactate production. And then this is just an example of what can be achieved with the higher gradients on the system. So this is Sharon Portnoy, who used to be in Greg Stanish's lab, using actually the same in vitro models, so those leukemia cells. So on the top are the untreated ones, and then on the bottom, the ones treated with the chemotherapy drug. And if you use just a standard diffusion sequence, the timings of this really target more things like cell density and cell size, which can be useful. But if you're interested on what's actually going on inside the cells, you typically need gradients that are really close together. And this is difficult to achieve with hardware. So an alternative is to use these oscillating gradients, this like sinusoidal waveform that you see. But unfortunately, you lose some diffusion weighting when you do that. And so the higher the gradients that you have, the more diffusion weighting that you can get back. So Sharon used the higher gradients on the system to get up to higher diffusion weightings and to see the contrast difference actually inside the cells at these shorter timescales. And then finally, I just wanted to show an example of the NMR spectrometry work. So on the top, this is from the S-ground scanner. So this is an image of a rat brain, obviously, and a voxel has been placed to do spectroscopy on this area of the hippocampus. So you see that along the top, and you might notice that it's a somewhat noisy spectrum, and some of the line widths are fairly large. So in some rats, we dissected a portion of the brain in the hippocampus and sonicated it and extracted the liquid portion using a centrifuge. And when we scanned that on S4, I mean, you see some slightly different metabolites because obviously there are things that are different when the mouse has died. But also you see better SNR and then some narrower line widths. So this is partly due to the fact just that this is a liquid as opposed to the semi-solid tissue. But also when you have that extra shim stack in the magnet on S4, you can get pretty good line widths. So that's a bit of a whirlwind tour of some things that people are doing. But the basic summary is if you're interested in using the Bruker system, you can email me, my contact's there, or if you can find me, I sit in like the very back corner of S605 as well. But a summary of what I would probably tell you is if you're interested in just observing, so anyone can do that from the console room, and then the qualified operator is responsible for making sure that no one who hasn't been screened or approved is going into the room, but the console room, into the magnet room, but the console room is fine for anyone. If you need to enter the scan room, then you need to do MRI safety training level 1 on My Education. So unfortunately, rotation students don't have access to this, so they're not able to enter the scan room until they've actually chosen a supervisor and complete the MR screening form. So if you've done this for the clinical scanner with Ruby, it's the same procedure. You just have to show me the documentation. And if you're just doing a few scans, I can help you operate the scanner. But if you're doing more long-term stuff, you probably want to become a qualified operator yourself. So this is the level 2 training on My Education and the screening form. And then there are some SOPs. And then I typically do just a safety walkthrough to make sure people know where like the important emergency buttons are or what any alarms mean. And then the hands-on training is really what takes the most time. So for a lot of the FUS labs, Shanghai has been doing this training because it's quite lab dependent what people need to learn. But if you're in one of the MRI labs, likely I'll be sitting down with you for a few sessions just to run through things because it takes a while to pick up on things. So that's kind of the overview that hopefully is helpful for new students. So I'll talk in a little bit more detail now about a few aspects of the system. So firstly, coils. So the reason we have these different options is that you want a coil that's going to cover the field of view, but that you're interested in. So you choose as small a coil as possible to get the SNR that you need, but if you go too small, then you might not be able to reach the depth that you need. So this is the main trade-off that people are interested in, but it's with the small bore scanners, it's also worth keeping in mind that there are physical limitations of the setup. So if you're interested in imaging mouse abdomen, for example, some of the coils probably won't fit in the scanner with a full rat. And then potentially also speed of setup. So if you're mainly interested in whether or not there's a tumor growing and you have a lot of animals that you need to screen, it might be simpler just to use the volume coil, even though the SNR isn't very good. So here are the Bruker coils that we have, or the Bruker proton coils, I should say. So this is on the top left is what the Bruker volume coil looks like when it's outside of the scanner. It should be inside the scanner when you get there because it's the only coil of these that actually is able to transmit and excite a signal. But usually it's used in combination with one of these receive coils. I've just called them colloquially here by the names. Like I call this the brain coil and this the linear array coil, but any of them can be used to scan brains. So in this case, the brain coil is a quadrotor coil that's located in this like front smaller bit here. And the linear array is a 2x2 array. So there are 4 little coils in a square in this top bit here. And you can see that these are about like 3 centimeters high. So that's why I was saying like you might not be able to fit that and a rat on top. Like they fit over top of the brain, okay, but maybe not other aspects. So in that case, or if you're scanning something smaller, you might be more interested in surface coil. There are 3 shown here, but the only one that we have for general use is the 20 millimeter surface coil. And then just a few more details. So the volume coil is tunable. So these little sticks that you see on the back are the capacitors for tuning and matching. So it's designed to be tuned for anything from unloaded up to a rat body load, which they say is 450 grams. So there are a few groups that have rats larger than this. And if you have that, it may be the case that even though the rat physically fits into the coil, you might have problems trying to get good tuning. And then the brain and the linear array coil are both designed for a rat head, and the surface coil for in vivo, like whatever the field of view is, in vivo tissue coverage. And then I've listed here from the Bruker documentation what they claim the SNR is. So you can see much lower for the volume coil than the brain and the linear array. The brain and linear array are similar, and then the surface coil is the highest of all. But they don't have a standardized ROI that they're measuring this over, so it depends on the depth that you're interested in. So just to give a little bit of an idea, these are, I think this is a rare image, so from the rare sequence of just a homogeneous phantom. And I've tilted it just so that the coil is here on the left side, and you can see the signal intensity falls off as you move toward the right. And so that lines up with this distance from the coil from left to right on each of these graphs that you see here. So the volume coil, as you'd expect, is pretty homogeneous all the way across this kind of 3 or 4 centimeter distance. But you see that the brain coil, although it has lower SNR than the linear array close to the coil, as you might expect, it maintains a good signal out to a slightly further distance. So you can probably use this coil for things that are like 3 centimeters deep or so, whereas the linear array, the signal falls off a little bit more quickly than that. And then the surface coil has even better signal close to the coil, but again, falls away quite quickly. So that's just to give people an idea of what coils might be useful for them. But obviously this doesn't suit every application. So Peter Trong in Jamie Neer's lab has been working to develop a range of surface coils, so they have different sizes and might work for different applications. I think the main one in regular use right now is this 55 millimeter diameter coil that he designed. Moses is using it right now for cardiac imaging and guinea pigs. But he also has a few other coils here that are a little bit smaller. And he wanted to point out that he is going to buy housing for this coil. So because it's the new one that he built most recently, it's kind of taped up right now, but there is like this black plastic housing that he is going to put on the bottom. And there's a cover that goes on all of these so that they go into the scanner. But this is just to show you the electronics and what they look like. So you might notice, for example, here, these last 2 coils have 2 connections. And this is because they actually have a preamplifier on board right next to the coil. So this should reduce noise. So in this case, you get the signal from the coil and it runs back through this wire, and you would attach a preamplifier back here. But this might add some noise into the system. Here, the preamplifier is right on board, and you can connect a second preamplifier and actually do 2-stage preamplification. So what does this look like actually in the scanner? So this is what the back of the scanner looks like. So the bore of the scanner is up here and your coil comes out the back. So if you're using one of the Bruker coils, they typically plug directly right into this orange low power proton socket. But Bruker also sells an adapter. So this is sitting at the back of the scanner and it plugs into this socket. And then I think there's like N connectors here and some BNC connectors. But what Peter's done is he has designed this adapter for the adapter. So it has this connection here that plugs into plugs into the adapter. It's meant for the phased array, but in this case, he set it up so that you can access different signals. So you plug your coil into the RF, and then you see there are these connections labeled pin. So those are for active detuning. So when you put a receive coil in, you don't want it to be active while the transmit signal is happening, because the signal is too much for the receive coil to handle. So the scanner sends a signal to decouple through these pin connections. And then there's also these DC connections. So those are for powering those preamplifiers that I talked about. And then I just want to note that you can see here that Peter's put a capacitor on the loop on this inductance. And this is actually a tunable capacitor. So what he's been doing with Moses is to actually tune the coil on each guinea pig before it goes into the scanner. So as opposed to some of those coils that are more designed for a brain load, you can design it for the load that you're particularly using it for in this case. So this is just like qualitatively what some of the results look like. So initially, this is the guinea pig with the 2x2 linear array coil. So this is the chest of the guinea pig, this bright area. And then in behind, you see the heart. So the bright is the blood inside the two chambers of the heart that you can see. And then the gray is the cardiac wall. And so the front half of the heart, you can see fairly well, but the back, you see that the SNR has dropped off a lot. And then with the surface coil, you see maybe a slightly lower signal toward the back of the heart, but it's relatively good the whole way through. And you can even see some of the vessels in behind the heart. And I would just note that it's not even all about surface to noise ratio. These three dots that you see along the bottom are the water blanket. So when you put the linear array coil in, the animal is actually sitting up off of the water blanket, and you're relying on like the back half of the animal and there's the air temperature to heat the animal. So some of these animals were getting fairly cold, whereas with this coil, they can be right up against the water blanket. And it's also become much easier to set up. So we tried the animals on their back and we had problems with that. And then we had them on their front, and it was difficult to get them centered over the right part of the coil. You can see also that it doesn't really fit very well into that little 2x2 array slot. It's not designed to hold a chest cavity. It's more designed for a rat brain. And so often things wouldn't be located quite where they needed to be. And we would have lots of problems trying to finish the pre-scan and get the right signal and get it to shim. There's a lot of fat in this field of view, especially when you're losing a bunch of your water signal at the back. Also, since getting the surface coil, I don't know if we've had any of the pre-scan errors that we were running into trouble with before. So yeah, I guess just an important lesson that it's worth talking to Peter if you need a coil for a particular application, or I think there are also a few other groups interested in developing coils. So that's everything that I had to say about coils. I also thought I would talk a little bit about the B0 field from the scanner and shimming. I did threaten when Rachel asked me to give an MR group talk to give an entire talk about shimming, because I feel like I spent half my time on the scanner doing it now that I'm doing spectroscopy. But also I didn't really think I had anything profound to say about it. So that's why it turned into this talk. So for those of you who don't know, the B0 field is inhomogeneous. Some of this is just the nature of magnetic field. Like if you imagine that you have your coil and the magnetic field lines running through it, the field is obviously going to be stronger at the center of that coil than at the edges. But that's not so much what we're talking about here. Like you see that even on clinical scanners, when you scan with a large field of view, you get distortions at the edges. But what's really more of interest here is that when you put something into the scanner, you get distortions anywhere that there's susceptibility, so at air tissue interfaces. So that's what I'm trying to show in these images here. So on top is a sagittal image through a mouse brain. So the nose is at the right side of the image and the back of the head is at the left. You can kind of ignore these darker lines. This is just an artifact of this multi-slice scan that was done. But this big blob in the middle is the brain. And if you acquire a B0 map, so this B0 map goes with this reference image. So that's why I have both of them here, just so you can tell where you are. And where you have air tissue interfaces, you see that there is a big change in the B0 in those areas, as you would expect when you have susceptibility. However, you might also notice that the B0 field is slightly different at the back of the brain than it is at the front of the brain. And these sorts of differences can cause distortions or signal losses, particularly if you're running an echoplanar imaging sequence. So because you're going back and forth in K-space over this long period of time, looking for phase accumulation, any sort of difference in B0 is going to accumulate errors and create these sorts of distortions that you see. Inhomogeneous B0 can also create problems for fat saturation. A lot of fat saturation methods rely on knowing the frequency of fat or water, and if that varies over your image, it can create problems. And then, as I mentioned, it's also important for spectroscopy. So in spectroscopy, you're looking for the frequencies of different metabolites. But if you have frequency differences that are instead related to just the location of, are just related to the B0 differences, then you get higher line widths that can create problems for trying to resolve metabolites that are close together. So some of this can be fixed in post-processing, like some of the distortions from EPI, but to be a little bit proactive and to try and do it up front, you can do what's called shimming. So this comes from shim coils, which in the case of the Bruker system are integrated into the gradients. And so the point here is mainly that these are actual physical coils. So there's kind of a limitation of what you can do with them. So the Bruker system has linear and second order shims, and you're trying to put different currents through these coils in order to adjust the local magnetic fields, so it's more homogeneous in the area that you're interested in. These shim coils are often symmetric, or there are asymmetric designs, but usually what this means is that it's easier to shim things that are toward the center of the scanner. And I did just note here that the last set of shims automatically load. Even if you restart ParaVision, which is something we tell people to do if they run into problems, restarting ParaVision resets most things, but it actually doesn't reset the shims. It assumes that whatever you're scanning this time is really similar to what you were scanning last time. So if the shims, if someone scans something with a lot of fat in it or they got really messed up, you might need to go in into ParaVision and reset the shims manually. So if you're using the scanner, you might be shimming without even knowing it. Hopefully you do know it, because I try to go over it with people just so they know what's happening during the pre-scan, but there is this FID-based shimming. So when you first put your sample in, there's sort of this general non-selective RF pulse, and they look for a signal at the proton frequency. So what you can see here is that there's this very broad peak. There's actually like 2 peaks. So there's something very strange going on with this magnetic field. And this would also correspond to a fairly a signal that decays fairly quickly in time, so in the FID. So the scanner does sort of this trial and error method, this iterative method, where it loops through the different shim coils and attempts to maximize the FID area, or alternatively narrow this frequency peak to get it as narrow as possible. So the default is to loop through just the standard linear shims, so the X, Y, and Z shims. And it does this first at like a very broad step width, and then a medium one, and then a narrower one. Usually this is pretty sufficient for most applications, as long as it finishes. However, if you do have something really fatty or strange in the scanner, you might see an extra peak here, and the scanner might have trouble trying to deal with it. So it is possible to shim manually. I haven't had to do this with anyone yet, so it'll be an adventure if it has to happen, but that's possible. As I mentioned, there are also higher order shims available, and you can use this FID-based method with those. You can add those in the adjustments panel, but most people don't do this, firstly because it's not usually necessary, but also it's relatively long to iterate through these things over and over and over again. So if you need higher order shims, typically you would use what on Bruker is called map shim. So different scanners have algorithms that work like this, and this is what you typically use if you need to do extra shimming for EPI or spectroscopy applications. Just to explain a little bit how this works. So you're going to acquire a B0 map, similar to what I showed before. And this can be done for any scan in the adjustments tab. And it starts a double gradient echo sequence. And the phase difference that is accumulated between those 2 echoes is going to be proportional to the local B0. So that's what's shown in this image here when you get a B0 map. And so the idea then is for the shims that you need the current through those shims to automatically be calculated in order to minimize the B0 in a region that you select. So if you're doing spectroscopy, you're probably going to select a voxel like I've shown here, and we want the B0 variation to be as little as possible here. If you're doing EPI, usually you would set an ellipsoid area, and you want it to be inside the brain, so you don't want to go near these air tissue interfaces where you can't really fix those B0 problems, but within the brain area, as big an area as you can get without approaching those, and try to minimize the B0 variation along there. And so the advantage of this is that it's much faster than iterating through the hardware, but it does rely on Bruker's algorithm that they have and a calibration that they ran when they set the scanner up to know how the shim coils relate to the magnetic field variation. So it's a bit of a black box, but it seems to work relatively well. So just a few things to know if you are having problems shimming. As I mentioned, having the thing that you're interested in central matters. I tried to pull up images that would demonstrate this, but I didn't actually have anything that was too much off center. I think you could say maybe that there's a slightly worse shim in this brain, but for things that are relatively close to the center, it does well. But if you are having problems, just make sure you're near the isocenter. And then there are factors affecting your B0 map. So the default parameters are pretty good in most cases, but you can change these echo times or your voxel size if you find out that you're getting too much dephasing or you don't have a lot of signal or something. And then I just want to note that Wilfred discovered that there's an automatic calculation for the line width that we sometimes use to check the shimming in spectroscopy. And actually, this doesn't give you consistent numbers. So I'm not sure why this is. I've looked into the code and it looks like it should give you consistent numbers, but sometimes it seems to sort of get stuck and just give you the same number and over again. So you might want to be running a manual check instead. That's something to be aware of. And then the final thing that I wanted to talk about is just the gradients, and in particular, the question of what is good gradient performance. And this basically came up firstly because of some work that I was doing with Moses trying to implement a diffusion sequence for cardiac imaging. But I also saw a pretty good talk on it at last year's ISMRM. So there was this standardized measures and benchmarks session, which maybe doesn't sound too exciting, but it's kind of an interesting idea of like how we can standardize MRI for it to become more widely acceptable. But there was a particular talk by Brian Rutt about gradient performance and the numbers that vendors report. And I guess I'd done a lot of diffusion work, so I thought I knew about gradients, but it's kind of different if you're comparing different systems or if you're trying to make a decision about what system to use, what system to buy, how do we compare apples to apples? So normally scanners will report, or vendors will report a gradient strength. So I'm showing here for the insert that we have 660 millitesla per meter, and then for the larger gradients that Moses was using, 300 millitesla per meter. And then a slew rate, so how fast can you ramp up to the maximum gradient strength, which also differs between these two. And then normally there'll be some kind of claim about the linearity of the gradients or geometric distortion. The particular document that I took numbers from here didn't have an exact number, but you'll often see like there'll be some kind of grid phantom, and the vendor will check that the distortion on this phantom is within their specifications over a particular field of view, and they'll give you that number. So those are the things that are typically reported, but these aren't always the things that matter. So in particular, if you're interested in diffusion imaging, it's important to note that the gradients can't be on continuously. I did kind of know that, so there is a duty cycle that's often reported, and you can check the duty cycle on the gradient scanner to make sure that you're not going over what's recommended. But perhaps more useful is this measure of maximum DC gradient value, which actually Bruker does report. I just didn't look it up before we started scanning with Moses. So on these small gradients, it's 330 millitesla per meter, simultaneous all channels, which is a little bit confusing, but I think what that means is you can run all of the channels at 330 millitesla per meter. So if you do that, then combined those three channels would give you something like 570 millitesla per meter altogether. So this is 80% of the reported maximum gradient strength. So maximum gradient strength is like what you can hit if you're just going briefly up to that, like if you're using it for EPI just to move through K-space, for example. But if you want to leave it on for a diffusion sequence, you're at like about 86% of what is reported to be the max gradient strength. And this is what Wendy, who was my predecessor, told me before she left. She told me you shouldn't run the gradients at more than 80% of maximum. And so I remembered that, but it turns out that this is really only true for the small gradients, which again, this is in the documentation, but I just didn't realize. So the DC gradient strength for those larger gradients that Moses was using was 115 millitesla per meter, which means if you have all the gradients on, you can only hit about 66% of the reported maximum. So the scanner will let you prescribe at like 100%, but I'm not sure if during a normal diffusion sequence it will throw an error, but we were using a custom diffusion sequence that had been written and it didn't throw any errors. It would just start running and then at some point it would stop. And we thought that perhaps we had a coding error. The pulse programming that we had done wasn't correct. But we eventually figured out by running at different gradient strengths, you could run the sequence and it would finish at about 65% for a spin echo diffusion, and 70% for an API diffusion, which is probably because the duration was a little bit shorter on that sequence. Yeah, it took a few weeks to get sorted out, which is unfortunate, but that's why it's, I guess, kind of important to keep these things in mind. So if you are using these larger gradients, diffusion is quite challenging. And then I did just know, so some scanners will also tell you a little bit about their gradient cooling. So the fact that the scanner kind of just shut down without any error is it probably has some temperature check where it knows like, oh, these gradients are getting too hot. So it shuts down, but it doesn't really tell you anything. It just stops the scan. And then the other gradient thing that I wanted to talk briefly about is something called pre-emphasis. So this is related to eddy currents. So when you turn on the gradients, some current runs through those coils. And because it's a time-varying current or time-varying magnetic field, this induces currents sometimes in the surrounding equipment in the scanner, but also it can induce it in the subject itself. And these time-varying currents counter the magnetic field gradient that you're trying to get. And so the gradient output isn't the intended one that you wanted. And so this is the result of eddy currents that often result in distortions. So Bruker, so you can fix this with something called pre-emphasis, or at least counter it a little bit, where you alter the current that you put in so that it counteracts these eddy currents and you get something closer to the desired gradient output that you wanted. So Bruker checks this pre-emphasis every year, this calibration, when they come for preventative maintenance. And I'm not quite sure what their report means. So it does tell you for each of the directions, the delay in milliseconds and residual B0. So I assume that's something like something related to the slope of this curve. But a question that came up, so this past year when they did it, they said it's still within specifications, but it's much worse than it had been the year before. So I was talking with a few people about whether it's something we should be checking on more often and how we might be able to do that. So I don't have access to the actual service that Bruker runs, and I wouldn't be able to actually change it, but we would know if something had gone wrong. So for anyone who doesn't know, I do run a monthly QA, but currently this QA is designed mostly to check on the coils and to check that they're still functioning. Oh, and I guess I should have mentioned that actually the 2x2 linear array does have a couple of flimsy elements that I'm trying to get in contact with Bruker to fix, but that's an ongoing story. So we run a few different sequences, like a multi-slice multi-echo sequence, a T2 weighted rare, a T1 weighted flash, and this echoplanar imaging sequence. And we check the SNR and the ghost level from each of them. So these are like the ghost levels somewhat related to other aspects of the scanner, but it's mainly designed to check the coils. And then we do also run a B0 map and a localized shim and check the line width from a voxel. But because this phantom is pretty homogeneous, it's, I think, not the ideal check for the shims, but you know if they run or not. So one suggestion was that we could add some kind of check for the gradients to this monthly QA. So something, for example, that where you would run the gradients pretty at like a high level, so a diffusion weighted EPI sequence. And then, for example, you could have a phantom with a known diffusion coefficient, like an ice water phantom. And as long as the diffusion coefficient that you measure over time is constant, you can be pretty assured that the gradients are working somewhat the way that you want them to. So I did run this once, but the diffusion in ice water is still relatively fast. So actually, I think I used gradients that were too high and I was getting slightly noisy images. So I need to go back and rethink this, either to run high gradients but short ones, or maybe to get a different kind of phantom. But if anyone has any experience like thinking about QA to run on gradients or has any ideas, I'm certainly open to hearing that. So I think that's everything that I had today. It's not really a conventional scientific talk, but just to reiterate, if you're interested in scanning, you can contact me. It's important to get the right coil for the right job. The standard linear shims are pretty good for most imaging cases, but there is this higher order shimming that's available via Mac shim. All I can really say about it is it seems to be a bit of an art form. The typical gradient specifications that are reported can be misleading, so it's important to think about those. Thanks.